A breakthrough for scientists after they had a 20-minute conversation with a humpback whale. Did it say, "I'm tired of fish? I'm tired of plankton"? So this team, including a professor from UC Davis, is hoping for more interspecies dialogue following this groundbreaking exchange with a whale named Twain. For 60 years, science filed sperm whale clicks under noise. 21 signals, nothing to read. Then 9,000 recordings went through machine analysis and came back with 156. Each one built from parts that can be rearranged the way our own words are. Feed that finding to Grok. Ask it what the structure actually implies, and it lays out something no journal abstract states plainly. This is not a signal set. It has the architecture of a language. Off Alaska, a humpback named Twain has already held a 20-minute conversation with a boat. A group of scientists had a 20-minute conversation with a female humpback whale. And they say this is just the beginning. So, what has been talking down there for 30 million years? The 20 minutes that broke the rule. The water was calm that day, which mattered more than it sounds. Surface noise contaminates playback experiments. Wind chop alone can smear the interval data the whole test depends on. The team had waited for conditions like these. They were working with the SETI Institute, the University of California, Davis, and the Alaska Whale Foundation. They were not there to record whales. Recording whales had been done for 60 years. They were there to speak to one. The sound they lowered into the water was a humpback contact. The vocalization humpbacks used to announce presence, the closest thing in their repertoire to a spoken hello. We said, "Hi, hi, hi, hi." Next time you want to say, "How are you?" It had been captured the previous day from a small group in the same waters. A group including a female the researchers knew by name and by history. Twain, 38 years old, cataloged, photographed, tracked across seasons. There is a real possibility they played her own voice back to her. The realistic expectation was modest. A whale might approach out of curiosity, vocalize once or twice toward an unfamiliar sound, and lose interest. A short investigative response would have been a good day. The speaker went in, the call went out. Twain came. She surfaced near the vessel and began to circle it slowly, keeping the boat inside her turn. Then she vocalized, not a random burst, but a contact call. After our 20-minute period of playbacks was over, we had turned off our speaker, and she continued to vocalize back to us even as she was leaving. It was like, "Hey, maybe another time we could meet up, or who knows, right?" Directed at the source of the sound she had just heard, the researchers played the call again. She answered again, and she answered again. Call, reply, call, reply. 36 exchanges across 20 minutes. A wild animal in open ocean, holding a structured back and forth with a group of humans on a boat. Dr. Brenda McCaughan of UC Davis, who led the work, described it as what they believe to be the first such communicative exchange between humans and humpback whales conducted in the humpback's own signaling system. But the response itself was not what unsettled the people on board. It was the clock. Humpback exchanges have a rhythm. Between calls, there is an interval, a conversational gap, the window in which the other animal is expected to come in. Twain did not vocalize over the playback. She did not answer early. She waited for the gap and filled it. Then the team did the thing that turned an anecdote into data. They varied the interval, lengthening and shortening the delay between playbacks. Her latency tracked theirs. When they waited longer, she waited longer. When they came in faster, so did she. Twain knew when it was her turn. Turn-taking is one of the load-bearing features of human conversation, and not something an animal produces by accident 36 consecutive times while adjusting to a changing tempo. It requires treating a call not as a sound, but as a slot, and understanding that the slot has an owner. That afternoon would be remarkable standing alone. And it is not even the strangest thing here. The larger work was already underway in a different ocean on a different species. And it had begun years earlier with a stranger stopping in a hallway. The stranger in the hallway. Marine biologist David Gruber was in his office at Harvard's Radcliffe Institute with headphones on, going back through old sperm whale recordings he had collected years earlier in the Caribbean while working on something else entirely. The sounds in his ears were clicks, rapid, mechanical, fired in short bursts with particular gaps between them. He had heard them hundreds of times, and every previous time he had taken the headphones off and moved on because the field had already decided what they were. Simple signals, an animal announcing something basic to other animals. Then Shafi Goldwar walked past the snort's open door and stopped. Goldwar is a cryptographer at MIT, a Turing Award winner whose career has been spent on the mathematics of concealed information, the structures governments use to hide their most sensitive communications. She listened from the doorway. Then she asked Gruber a question that redirected a field. It sounded, she told him, like Morse code. Had anyone tried running it through machine learning? She was not making a poetic comparison. Someone who spends her life recognizing the fingerprints of encoded information heard an animal noise through a doorway and registered it as patterned in the way that carried content is patterned. And the answer was no. Across decades of citation research in every ocean, nobody had applied the kind of analysis used on an unknown code. The recordings had sat in archives for years, cataloged, filed, described, never decoded. The work that followed produced results dense enough that for a while almost nobody outside the field could read them either. Then the machines that read language arrived. The machine reads. Grok is xAI's conversational system launched at the end of 2023 on the same broad architecture as the other large language models of that window. What such a system actually does is worth stating precisely. A large language model is not a database and not a search engine. It is a statistical structure trained on enormous quantities of text, learning which patterns follow, which until it can generate text fitting the shape of what it absorbed. What it is fundamentally good at is structure, recognizing it, describing it, and translating between one technical vocabulary and another. That is precisely the kind of machinery the whale problem needed, and precisely the kind of machinery that had never been pointed at it. The sperm whale findings had been published in the way findings are published in journals in the language of acoustics and computational linguistics dense with spectrogram figures and interclick interval statistics. They were public and for practical purposes sealed. Reading them required knowing what a formant is, what rado means in a click train, what duality of patterning implies. The information existed, and almost nobody could reach it. Conversational AI changed the access problem, not the science. Asked to explain the code of features and why researchers consider them significant. A system like Grok lays out the 4 variable elements, maps them against the equivalent concepts in human phology, flags which comparisons are structural and which are speculative, and takes follow-up questions until the picture holds. Pressed on where the evidence is thin, it says so. None of that is discovery. Every finding here was produced by researchers with hydrophones, tags, boats, and years. What the machine did was collapse the distance between a specialist result and a general audience. And results that reach a general audience get pressure applied to them from directions the original researchers never anticipated. Questions get asked in public that would otherwise have stayed inside a conference room. And when the code of findings are laid out plainly in order without the hedging apparatus of a journal abstract, they describe something that is not supposed to exist outside our own species. The machine that read the ocean. Goldasser's question needed 2 things to become an answer. Enough computing power to find structure that human ears cannot hold, and enough data to feed it. Gruber brought in AI researcher Michael Bronstein, who argued that the same class of deep learning architecture behind language models could in principle be pointed at a non-human communication system. Text models learn structure from enormous quantities of text. Point the same machinery at enormous quantities of clicks, and the structure, if it exists, should surface. The catch was scale. Nobody had that much whale data because nobody had ever tried to collect it. Music in 2020, the effort was formalized as Project CEI, the Citation Translation Initiative, pulling in researchers from MIT, Harvard, UC Berkeley, and more than a dozen other institutions across biology, robotics, linguistics, cryptography, and machine learning. They chose the waters of Dominica, and the choice was deliberate. Project SEI has turned to the Caribbean and the island of Dominica to record as many clicks as they can. It is one of the few places on Earth where multi-generational sperm whale families return reliably season after season. These were not anonymous animals passing through. The families were known, the matriarchs had names, and the social structures had been tracked for decades. It was the closest thing to a neighborhood that whale science had ever had. What went into that water was unlike any previous marine acoustics deployment. permanently moored hydrophone arrays along the routes the families used. Bologing tags attached to whale skin with suction cups, each carrying multiple synchronized microphones so individual voices could be separated out of a group conversation. Depth sensors, accelerometers reading body orientation to a fraction of a degree. The point was not to hear whales. It was to know for every click who produced it, who was nearby, what that animal's body was doing, how deep it was, and what the rest of the group was doing in the same second. Sound plus context. That is the difference between a recording and a transcript. Roughly 9,000 recordings went into the analysis. Here's what the field believed going in. Sperm whales used about 21 distinct click patterns called codas, each carrying one fixed meaning. The standard analogy was a traffic light, a small closed set of signals, each meaning one thing. No combining, no layering, no building. The analysis did not adjust that picture. It demolished it. The system identified 156 distinct codas. But the count is not the finding. The finding is what sits inside each one. Every coda proved to be built from features that can be varied independently. Tempo, the overall speed of the click train. Rhythm, the arrangement of gaps between clicks, whether bunched or spread. Ornamentation, extra clicks inserted at the edges of a pattern. And rub, small elastic variations in timing stretched across a sequence. The acoustic equivalent of a voice tightening or loosening. Vary the parts, and the whole changes. That is not a set of signals. That is a combinatorial system. A small number of basic elements recombining to produce a much larger space of possible messages. Asked to compare those features against human phonology, Gross surfaces the parallel that linguists reached independently. Human speech takes a few dozen individually meaningless sounds and recombines them into an unlimited number of meaningful units. Linguistics calls it duality of patterning, and it has long sat near the top of the list of features separating human language from animal signaling. The analysis found it operating in an animal clicking in total darkness, half a mile below the surface. And if codas are built from independently variable parts, the inventory is not fixed. New combinations remain available, meaning the system, music, can in principle produce a message that has never been produced before. A closed signal set can only repeat itself. The architecture here permits novelty, and novelty is what separates a vocabulary from an alarm. Then the analysis turned up something that had nothing to do with vocabulary at all. The whale that changed its voice. The same individual whale produced measurably different patterns depending on which other individual it was addressing. Linguists call that audience design. It is why a person speaks differently to a child than to a judge, and why a sentence softens for someone who is grieving. It is not a vocabulary skill. It requires a working model of somebody else's mind. An understanding that the listener has an inner life that is not yours and knows things you do not. Pressed on that finding, the system lays out the implication in order. Adjusting a message for a listener requires representing the listener. Representing the listener requires holding that other minds exist. That is the entry criterion for what psychologists call theory of mind. A threshold our own species does not cross until around the age of 4. If the finding holds, the whale data did not just contain grammar. It contained evidence of an animal modeling another animal's understanding in a species our science spent a century describing as producing noise. If something down there is adjusting its speech for whoever is listening, subscribe, because the KOD to meaning tests are the next thing to land, and they will either confirm this or take it apart, and there is a harder implication buried in it. Audience design means the message and the listener are linked, which raises a question nobody has answered. Across 2 centuries of contact, have these animals ever designed anything for us? The sound that should not exist. Gaspar Bush, a linguist at UC Berkeley, took the old Dominica recordings and did something almost nobody had done. He slowed them down and examined the internal shape of each individual click, the way a phonetician examines a spoken syllable. What came back should not have been there. The whales were producing vowels, not sounds loosely reminiscent of vowels, not rough analogs. Structures with the acoustic geometry of human vowels, showing the same relationships between resonant frequencies that define a vowel in any human language on Earth. B identified 2 primary types. One labeled the A vowel corresponds to the vowel in father. The other, The I vowel corresponds to the vowel in C. The recordings also contain what look like diphthongs, gliding combinations in which one vowel slides into another. The way the vowel in boy moves across its own duration slowed down and mapped the shapes lined up with human vowel space. To put it plainly, researchers used to think of whale communication as a kind of Morse code, and this analysis suggests the calls behave more like extremely slow vowels with a complexity closer to human language than anyone expected. Understanding why that is disorienting rather than merely interesting requires knowing what a vowel costs. Producing one requires a larynx sitting low in the throat, fine control of tongue and jaw, regulated airflow, and a resonating chamber reshaped in real time, so specific frequencies are amplified and others suppressed. That anatomy took millions of years to assemble under selective pressure, assumed to be pointed at speech, and was treated as effectively unique to our lineage. Sperm whales have none of it. Their sound system evolved in the deep ocean, in absolute darkness under crushing pressure for a completely different job. Echolocation. They send sound into the dark and read what comes back, building a picture of an environment they will never see. It is a sonar organ, not a mouth. It did not evolve towards speech in any sense. And yet music, run through the most sensitive acoustic analysis available. It produces structures that look functionally like the building blocks of speech. That is convergent evolution, the phenomenon that gave sharks and dolphins the same body shape from opposite ends of the vertebrate tree. Dr. Daniela Roos of MIT summarized the code of findings without ornament, saying the results show far more complexity than previously believed and that this challenges the current state of belief about the animal world. That may be the most restrained sentence ever written about a discovery this size. And there is a detail that rarely survives the coverage. The apparatus producing those vowel-like codas, the spermaceti organ filling the front third of the animal's head, and the phonic lips at the front of the nasal complex, is the identical apparatus that produces the hunting click. Sperm whales are the loudest animals on Earth. Their clicks measured at around 230 dB underwater. A jet engine at close range is about 140, and human eardrums begin to fail near 150. The warning that crossed an ocean. When American whalers pushed into new Pacific grounds in the early 19th century, the hunting went well. They found sperm whales easily, and their strike rates were good. The logbooks are full of it. Then, within roughly 2.5 years, the numbers collapsed. Analysis of whaling logs by researchers, including Hal Whitehead and Luke Randell, found strike rates in newly hunted grounds falling by around 58%. The whales had not left. They had changed. Animals approached successfully with one set of tactics began responding differently, moving upwind where sailing ships could not follow, abandoning the defensive circle that works against orcas and is catastrophic against harpoons. The shift outran individual learning because most of the animals doing it had never seen a whaleboat. The explanation the data supports is the one nobody enjoys. The survivors passed it on, not only to the animals beside them, but outward through a social network spanning music, clans, and ocean basins into groups with no direct experience of the threat. Information about a brand new predator moved through a non-human population faster than encounter alone could carry it. Historian Bath Sheba Demuth, working through 19th century whaling material, has described how the men on those ships recorded the change with something close to unease, writing that the animals seemed to be communicating with each other and that the younger whales appeared to have learned something they could not have learned firsthand. Sailors with no theory of animal cognition and no reason to be generous about the creatures they were killing watched information move through a species and wrote it down because they could not explain it. The same journals recorded something else filed under noise. When a whale was harpooned and dying at the surface, the rest of the group would often go still. Then the clicking would start again, and the sailors described it as different, denser, more intense, music unlike the routine sound of a foraging group. For 2 centuries, that was cataloged as distress, the acoustic equivalent of a scream. But these animals have 156 codas, internal grammar, and the apparent ability to tailor output to a specific listener. Whatever moved through the water in those moments was not undifferentiated noise. It was structured and it was aimed at somebody. Nobody recorded it. It was heard by frightened men on wooden ships, written down in a language that could not hold it. and it is gone. The pattern did not stop when the harpoons did. In the Galapagos, researcher Oscar Palacios and colleagues were running acoustic tracking on a pod of roughly 25 sperm whales. Data arriving cleanly. Then the data stopped. Not gradually, not one animal at a time. The pod went silent at once, and then was gone. Searching turned up nothing. The interpretation the music team reached is the one that is difficult to hold without flinching. They proposed that the whales had detected the monitoring equipment, communicated about it among themselves, and collectively stopped vocalizing. 25 animals agreeing on silence as a response to surveillance. It remains a hypothesis, but if it is anywhere near right, then 2 centuries apart, the same species has twice changed its behavior in response to being observed by us. And one of those times, we were on a ship it decided to sink. The ship that may have been answered. On the 20th of November, 1820, the Nantucket whale ship Essex was in the Pacific, roughly 1,500 nautical miles west of the Galapagos, music doing routine work. Then, First Mate Owen Chase saw something that did not fit. An unusually large bullperm whale was lying motionless on the surface with its head pointed at the ship, not feeding, not diving, facing them. It began to move slowly at first, music, then faster, then at full speed, and it did not turn away. It drove its head into the hull hard enough to throw men off their feet. Then it surfaced, came around, and struck the same section a second time. The bow was destroyed. 20 men went into 3 open boats in the middle of the Pacific with almost no water and almost no food. What followed ran for roughly 3 months and ended in thirst, starvation, and finally in the survivors eating the men who had died. It came home. The story became the seed of Moby Dick. Chase wrote his account within a year, music, and the strain in it is visible. He was a professional hunter who had watched many sperm whales die music and could not make this one fit anything he knew. He described the animal as acting with what looked like decision, noted that it came twice. The second time positioned to strike the damage it had already made, and wrote about its apparent fury and almost in the same breath the appearance of calculation. 2 explanations that do not sit together offered by a man who could not choose between them. Here is the part almost nobody knows. In the hours before the attack, the crew had been repairing a damaged whaleboat, hammering on the hull. Fast repeated percussive strikes, music, transmitted into the water through the wood. Researchers have raised the possibility that those strikes registered to the bull as click patterns, not as a threat, as a voice coming from inside the ship. The idea is a hypothesis and nothing more. No one can test the acoustics of a hull that sank 2 centuries ago. But if it is anywhere near right, then the most famous whale attack in history was not rage and not confusion. It was a reply. The Essex was not isolated. The Alexander was rammed and sunk by a sperm whale in 1851. The Kathleen went down the same way in 1902. Whaling logs across 2 centuries record music, sperm whales turning back after a strike, pressing coordinated attacks rather than fleeing, placing themselves between boats and calves. These were animals with the largest brains on the planet, decades of memory, and a network already shown to move survival information across an ocean in under 3 years. The behavior did not stop with sail either. Since 2020, orcas off the Iberian coast have been striking sailing vessels, specifically the rudders, bending and snapping them. By 2024, the tally music ran into the hundreds of interactions with a handful of boats sunk. Researchers traced the behavior to a small number of individuals, music, and watched it spread through the population, including to animals with no history of the original encounter. More than 30 scientists signed an open letter urging the public not to project human motive onto the orcas while stating plainly that they are socially complex. Music, that populations carry distinct cultures, and that the behavior is spreading socially. Nobody can currently say, music why? The explanation, if there is one, is moving through a channel that has not music been read. Before this goes any further, the case deserves its strongest opposition, and there is a serious one where the skeptics are right. Plenty of researchers think this story is running ahead of the evidence, and they are not being obstinate. Finding combinatorial structure in a signal is not the same as finding meaning in it. Bird song is highly structured. So is a modem handshake. Structure is what any system develops, when it needs to encode a modest number of messages efficiently. And no part of the code of work has yet paired a specific pattern with a specific reference under controlled conditions. Until then, calling it language is a decision about vocabulary rather than a finding. The vowel result faces the same objection. Vowel-like resonance can emerge from any air-filled cavity of the right dimensions, which a sperm whale's nasal complex certainly is. Acoustic similarity does not establish that the animal uses it the way we do, and a spectrogram cannot distinguish a word from a byproduct. Audience design is the most fragile claim of all. Whales in different social contexts behave differently, and behavior changes acoustics. Distinguishing a whale adjusting its message for a listener from a whale simply being in a different situation is genuinely hard, and the current data cannot fully separate them. There is also the oldest trap in the field. Machine learning systems find patterns because that is their function. Give one enough data, and music, will return structure whether or not the structure carries content. Human researchers, meanwhile, find human structures because those are the structures we know how to look for. A method built to detect language will, tend to report language. The conversational systems inherit that problem and add one of their own, which is worth stating without softening. Grok cannot verify acoustic data. It cannot listen to a hydrophone recording, cannot confirm that a cod means anything, and music cannot adjudicate between competing interpretations of the same click train. Asked directly, it says, so what it can do is organize published findings, explain the reasoning behind them, and flag where the evidence stops, which is useful and which is not discovery. The machine did not find anything in the ocean. It found the shape of what other people found and made it legible. So what would settle it? A confirmed KOD to reference result would have to look like this. A specific KOD produced in a specific context followed by a predictable behavioral response in other whales replicated across different individuals, families, and seasons. Then the reverse, that coda played back into the water, producing the same response in animals not part of the original observation. Prediction, not correlation. Repetition, not anecdote. Nobody has done it. The Twain playback is one route toward it. Nothing has produced a confirmed word, which makes one particular pattern, the one researchers have been willing to guess at either the beginning of everything or a very expensive coincidence. The first word out of 156 codas, one turns up more than any other in the Eastern Caribbean clans. Researchers write it as 1 + 1 + 3. 2 isolated clicks, a pause, then 3 faster ones. It appears everywhere before deep dives on surfacing when groups converge after hours apart around births. It crosses situations with almost nothing else in common. Exactly the profile expected from a phrase that is not about any particular situation. The cautious proposal is that it means something close to I am here. Not a warning, not information about food or predators or depth presence. One animal telling another that it exists and is nearby. If that is right, the first thing we may have understood a sperm whale to say is the first thing almost every social species must be able to say. It has been said in every ocean for something on the order of 30 million years. Through the entire evolution of the primate line, and through the 2 centuries in which we killed these animals in industrial numbers while filing the sound under noise. Commercial whaling killed several hundred 000 sperm whales, music in the 20th century alone, and ship strikes still kill them every year. If the code of work holds, those were not simply animals. Each one was a speaker carrying part of a record, and every strike ended a sentence somewhere in the middle of it. The ocean has not gotten quieter since. Shipping noise, sonar, and seismic blasting now saturate an environment where sound replaces sight entirely. And at sufficient intensity, underwater noise causes hearing damage. The phrase researchers use is blunt. A deaf whale is a dead whale. The law has begun to register the implication. In 2024, Maori and Pacific indigenous leaders from Aotearoa, New Zealand, and the Cook Islands signed a treaty recognizing whales as legal persons. Behind question directly, if human-like structures exist in whale communication, then what is language? Is anything about it uniquely ours? And what does that mean for the law? Somewhere in that ocean right now, the answer is being taught. Sperm whale calves babble. They produce messy, incomplete, badly timed attempts at the click patterns of their clan over and over, correcting toward the adult music form. Among the first things a calf gets right